So this video is going to be a follow-up to the trigonometric substitution video. So in this video we're going to be doing examples of trigonometric substitutions. So let's start with this example first. Integral of x squared over radical 9 minus x squared dx. So first we have to determine which method are we going to use, right? If you go back to our intro video notes, we had three cases. Which are right here. We have to make sure which case are we in right now. So when we look at this, the radical is 9 minus x squared. So that means it's a number minus a variable squared. And when you look back at our cases, the only one that has as being subtracted by is a number minus x squared is this first one. So the first case. So we're gonna be using this first case. So we're gonna be using sine theta, right? We can rewrite this radical as 3 squared minus x squared, and we are using sine theta is equal to x over 3, right? Because we need that x over a. Sine theta is equal to x over 3. When we solve for x, we get 3 sine theta is equal to x. And then the next step we need to do is actually take the derivative of this right here, because we're gonna need that when we're substituting back into the original integral. So this is just 3 cosine theta d theta, because the derivative of sine is cosine. So now that we have that, we can start substituting back in to the integral. So integral, so we see that there's an x squared here, so this is just gonna become 3 sine theta. So 3 sine theta, and we just add a squared over radical 9 minus, and then we see another x squared here, so we do the same thing. 3 sine theta squared. And then we said that right here we're gonna be switching from x to theta. So when we took the derivative of x, we got dx is equal to 3 cosine theta d theta. So we just plug that in for dx in place of dx. So this dx will turn into what we calculated. So this is going to be 3 cosine theta d theta. So far all we did was find out what case we're in, which we're in the sine theta case, and then we just rearrange the sine theta equals x over 3, so we get a value for x, an expression for x, and then we just take the derivative of that because we're going to need that for the dx. So the next step would be to simplify this a little. So let's get rid of those squares by squaring the 3 sine thetas. So we get 9 sine squared theta over 9 minus 9 sine squared theta, and it's going to be times 3 cosine theta d theta. So everything is in theta now. Next step you would do is actually factor out a 9 in the radical. So leaving this the same, over 9 minus 9 sine squared theta. right? That's what we had before. But when we factor out the 9, we're left with 1 minus sine squared theta times 3 cosine theta d theta. So now that we've gotten up to this point, now we can take the square root of all of this in here. And that's easy. That's just 9 squared theta up here. And then square root of 9 is just 3. And square root of 1 minus sine squared theta, we're just going to leave it as that. We're just going to leave it as that for now. So now what we can do is substitute in the Pythagorean identity for cosine squared theta. We have it right here. So this entire thing is just equal to cosine squared theta. Cosine squared theta. And we still have this 3 cosine theta d theta. Now we can easily take the square root of cosine squared theta, which is just cosine squared. And now we can cancel these 3 cosine thetas. Yeah, we can cancel these 3 cosine thetas. And we end up with, so let's go on to the next page. And what we end up with is 9 sine squared theta d theta. And we can pull out the 9 by the constant rule. And we get this. So integral of sine squared theta. So when we look at this, there's no obvious way to really solve this integral. But what we can do is actually use trig identities, another trig identity, to rearrange this integral so we can actually solve it. So the trig identity, the trig identity we can use is called the half angle identity for sine squared theta. And it's basically this right here. Sine squared theta is equal to 1/2 minus cosine 2 theta. So we can use that. So we can substitute sine squared theta for that and then solve. So let's do that. 9. So we get 1/2 1 minus cosine 2 theta d theta. Now that we have that, we can pull out the 1/2 by the constant rule. We get 1 minus cosine 2 theta d theta. And now we can take the derivatives, right? Now we can take the derivatives. So it's going to be 9 over 2 is outside. And the derivative of 1 is just going to, since we're in terms of theta, the derivative of 1 is just going to be theta. Derivative of cosine theta is going to be, let's see, 2 sine theta. 2 sine 2 theta. So like that. So this is what we get. Now, what we can do. So now what we have to do is actually switch back the theta into what do we switch to? So we need to switch theta back into x. Yeah, so we're supposed to switch theta back into x. So let's actually do that. So in order to do that, we have to determine what theta is, right? So when we look at what we have originally, which was sine theta is equal to x over 3, we see that in order to get theta, we need to take the inverse of sine. We need to find the inverse of sine in order to cancel the sine and try to solve for theta. So let's do that. So let's do sine inverse of sine theta, right, is equal to sine inverse of x over 3. These signs cancel and we're left with theta is equal to sine inverse x over 3. And now that we have theta, now we can start plugging back in to the original expression. So what we can do is so we know theta is, so let's write it right here. Theta is equal to sine inverse x over 3. So we can plug it back in. Theta x over 3. This is going to be minus 2 sine 2. So this is going to get a little confusing. So what we're going to do is make this sine 2 theta into another trig identity. We're going to substitute it with another trig identity. So the trig identity we're going to use, so for this, the trig identity we're going to use is sine 2 theta is equal to 2 sine theta cosine theta. So we're going to use that trig identity. So let's do that. We're going to get 2 times 2 sine theta cosine theta. There you go. So right now we have everything. We're getting close to putting everything back to x. Now we just need to substitute x for theta in this case, in this part of the problem. So we get in this parentheses we get 2 sine, we get sine inverse x over 3, right? And then we get cosine, and then we get sine inverse again, sine inverse I think there could be a better way. So this cosine theta, we could actually solve for this cosine theta as well. If you look back at the original function, So you know what, we're gonna keep doing what we're doing right now. So we'll just plug in x for theta. So we get sine inverse x over 3. Now we can simplify. This sine cancels with this sine inverse. This cosine and sine inverse, we're just going to keep it like that. So we get 2x over 3 cosine sine inverse x over 3. Distribute this 2 and distribute this 9 over 2 as well. So actually we don't need to distribute this 2 just yet. Just distribute the 9 over 2. And when that happens, these two cancel. And we get minus 9 times 2 x over 3 cosine sine inverse x over 3, and this right here is just 18, so let's just write 18. And this is basically our final answer. We just need to add the plus c, and this is the final answer basically. So the thing about trigonometric substitution is these problems take very long and involve a lot of algebra and trig, and there's going to be a lot of substitutions happening, so you have to keep track of if you're in terms of x, in terms of theta, in terms of u, and stuff like that. So let's do another example. So let's do this example right here. So we have to see which case we're in right now. So right now, this is written in the form x squared minus a squared. So when we look back at our cases, the only one that is x squared minus a squared is the case 3, and case 3 involves secant. So we're going to be using secant. So secant theta is equal to x over 2, because in this case a is actually 2. So secant theta is equal to x over 2. That means that x is a 2 secant theta. That means dx is equal to 2 secant theta tan theta d theta. So now what we can do is just substitute for the x's in the original integral, and we get, so on the top we get, so x is, we know, is 2 secant theta squared and minus 4 over 2 secant theta to the 4th, and dx we know is 2 secant theta tan theta d theta. Now you could simplify by squaring everything, and then taking the 4th power of the denominator. We get 2 to the 4th power is 16. Then secant 4 theta times 2 secant theta. Now what we can do is we need to actually do the Pythagorean identity. So first what we're going to do is take out a 4 underneath the radical. We're going to factor out a 4. And we're left with this. And we can substitute in for the Pythagorean identity. Secant squared can be turned into tangent squared. Secant squared theta minus 1 can be turned into tangent squared theta. So square root of 4 is just 2. And then we have square root of tangent squared theta now. And this is what we end up with when we substitute in the Pythagorean identity. Now the next step would be to simplify a little more. So the first thing we would do is take out this 2 and 16. When you simplify that, we just get 1/4. So we're pulling out a 1/4. And this tangent squared theta, if you take the root of that, the second root of that, you get just tangent theta. And then that's over secant 4 theta. Also, I forgot to pull out this 2 as well. So we're going to be pulling out this 2, these 2. So this is going to give us basically 4 over 16, which is just 1/4. We're left with secant theta, tan theta, d theta. We can cancel the secant theta with one of these secant thetas. And we get 1/4 over tangent theta over secant cubed theta, and the other tangent theta that is left. And we can just actually put these two tangent thetas together as tangent squared theta. So this is what we end up with so far. Now, in order to actually integrate now, we need to do some substitutions, use some trig identities. So this secant cubed can be turned into we know that one secant is just 1 over cosine, right? And say we switched secant cubed theta with cosine cubed theta. So let's do that. Let's try that. So let's say we substituted cosine cubed theta for secant cubed theta. This is what we get. And by the rule, like some of the rules in algebra, they tell us we can flip this over. Actually, we can flip this over into the numerator since the fraction is in the denominator. So let's do that. So we're gonna go on to the next page. And what we end up with when we flip that over is 1/4 over tangent squared theta cosine cubed theta d theta. So this is what we end up with so far, right? When we substituted the secant cubed theta in for the 1 over cosine cubed theta. Now we still aren't in a form that we can start integrating. So what we're gonna have to do is do substitutions for tangent as well. So tangent is just a sine over cosine. So what we can do is do this. Substitute in sine squared theta over cosine squared theta, because this is just that, this is just tangent squared theta. And then times cosine cubed theta d theta. And now what we can do is cancel these out, cancel out the cosines, and we are left with sine squared theta and cosine theta d theta. This is what we get so far, right? At this point, you might be thinking, oh, we could do trigonometric integrals or something like that. But no, there's actually an easier way. We could do u substitution here. We could do u substitution, since we could use u is equal to sine theta, right? And we know that du is just gonna be cosine theta d theta. We have that right there, and we have the sines as well right here. So let's actually do that. We could rearrange the sine squared like this, so it's clear that sine theta is going to be the u, and then we already have the du. So let's do this now. So we know there's a 1/4 on the outside. We see that there's going to be a u squared here, and then we know du is all this right here. And this is just simple this is simple power rule. So it's going to be 1/4 times the u squared. The integral of u squared is just u to the third over 3. And this is just 1/12 u cubed. So now that we did their integral and found this, at least the solution, now we have to go back to x, right? You have to go back to x. But first we're going to have to go back to theta, since we switched from x to theta, and then we go from theta to x. So what we're gonna have to do now is go from u to theta and then back to x. So first, let's go back to theta first. So 1 over 12 u cubed turns into 1 over 12 sine cubed theta. So that's what it turns into. And then when we turn into x, so let's say over here is u to theta, over here is going to be u to x. Now when we turn back to x, we know we're going to have to look back at the original substitution. So right here, secant theta is equal to x over 2. In order to solve for theta, we have to take the secant inverse. So we have to take the secant inverse. So it's going to be secant inverse of secant theta is equal to secant inverse of x over 2. This secant cancel, theta is equal to secant inverse x over 2. So right here we can write theta is equal to secant inverse x over 2. And we're actually not going u to x, we're going theta to x now. So let's do that now. Let's plug this into theta. So we get 1 over 12 sine cubed theta is secant inverse x over 2. Secant inverse x over 2. And then yeah, that's basically it done. This is what we get as the final answer basically. So this we just added plus c.